Hi, this is Discrete, section 4.3. We're going to deal with graphs and their vertices and edges. So the first problem we've done before, and we've talked about it, and we modeled a little bit, but we'll go through it again here, is that if we do the handshake problem, if everyone in this class shakes hand with everyone else, how many handshakes would there be? And so what we want to do is try to go out here and say, for instance, we have 14 people in the class. How many handshakes would we have? Well, how we can model that is that we want to start with 2 people, and we can connect them. This is a vertex edge graph because I have 2 vertices, which are the points, and then the edge is the segment that connects them. Then if I have n equal to 3, what I want to do is connect them like that. So continue on with this and try each one of these and pause and then come back to me and I'll have this up. So here are the diagrams that we have with n equal to 2, 3, 4. 5 is just based on the 4. So I replicated the 4 with the blue and then I just added in one more vertex. When I did that, I connected up all these sides to the vertices that I had before. And so what I'm doing here is that really I just added in 4 more segments here, which means 4 more handshakes. And from here, what I did was I added in 3 more handshakes. And from here, I added in 2 more handshakes. So what am I going to add in here? Well, if I look at this, I already had this blue thing from over here. And I just added in 1 vertex, and so the handshakes that I added in are 1, 2, 3, 4, 5. So I added in 5 more. And we can continue on this pattern. So if I go here, I'm going to add in 6. So I already have the 6. I changed this diagram to look like this. But then I added in a 7. So I added 1, 2, 3, 4, 5, 6 more handshakes. And that's what I said. Now what we want to do is try to find a rule for this, and we've done this before, but if I have n vertices, well, here I got 7 vertices, right? And so I take this 1 vertex and I connect it up with 6 segments to all the other ones. So that's 7 times 6. However, what happens is that if I connect from here to here, I double counted because I counted all the vertices, all the edges from this vertex too. So since I double counted, I got to divide this by 2. So in total, what I have here are 42 handshakes. If I do that here, 6 times 5 divided by 2, this would be 15 handshakes. Sorry, I forgot to divide this by 2. So this would be 21 handshakes. Okay, so when I have 7 people in the room, I'm going to have 7 handshakes. If I have my 14 people, like I said, we're going to go 14 times 13 and divide by 2. This would be the number of handshakes for 14 people in the room. Okay, so I can do this and use this formula for any number of handshakes that I do have. Regardless, more so in this section, what we're focusing in on are these vertex edge graphs. And so we have many applications of these vertex edge graphs, and you can find at least 2 that are in your book. So you should go and try and find that. Now, more practical example, well, not necessarily a practical example, but how we might use this. Here's an example from the book. Construct a graph with the following vertices and edges. So what they tell you is that we have these vertices here, A, B, C, D. So I'm going to plot these out. A, B, C, D, E. So this tells me I have 5 vertices. Now the edges, the E stands for edges. I'm going to connect up all these edges based on what they tell me. So they say draw segment AB. So I'm going to do that. I'm going to draw a segment AC. I'm going to do that. CD, DE, and DA, and BD. So there's my graph right there. Now, one thing I forgot to mention up above, which I need to go back and say, this right here is what we call a complete graph. I missed right over that, sorry. But this complete graph means that I take this vertex and I connect it to all the other vertices that are there. This is how we call this. We call this a K7. So if everybody shakes everybody else's hand, we have a K7. If we don't have everybody shaking each other's hands, we do not have a complete graph. And that's the idea that we do have here. That was the major point that I skipped over. Sorry. Now, if I look at this new graph that we just built, is this a complete graph? Has everybody shook everybody else's hand? And the answer is no, this is not complete. Because if you look at E did not shake A's hand. And as soon as you see that, you can say it's not complete. But more so, E doesn't shake B, E doesn't shake C, E only shakes D's hand. So it's not a complete graph. Now, what we might say is that if it's not a complete graph, what is its complement? When we talk about the complement is the edges that would be put in to complete the graph. So in other words, in this case, with the handshake example, we would say, who has not shook a certain person's hand? And that's what we want to look at. So E has not shook A's hand. So if we wanted to make this complete, that would give us the complement. So I'm going to draw here in green the actual complement that we would get here. So I'm going to take that edge, and then E to B, and E to C, and then I got to continue on with A to C. No, I got A. And so for B, I got to go to C, and then from C goes to D, E, A, B. So it looks like we are complete now. Now with this, anything in the green would be part of the complement. So I actually should have a green line here. Anything in the blue would be what we started off with. So the complement is just what do you need to add in order to make it a complete graph. And that's what we have here. So then the complement would be the edges then I got AE, BE, and then EC, and then BC. Those would be the edges of the complement that we would need. Okay? Then the next question is, this keyword here is adjacent. Adjacent means next to. However, in this representation, it does mean something a little bit different. Going back to my original graph right here, which vertices are adjacent to each other? Is E adjacent to A? You might say that because they're right next to each other. However, that's not how we define it. Adjacent means that they are directly connected. And so E is not connected to A, or else what you could say, to be adjacent, E had to shake A's hand. If not, then they are not adjacent. Okay, so if we do say which ones are adjacent, we have A and B are adjacent, A and C are adjacent, A and D are adjacent. Oh, this is just what we wrote out right here, isn't it? So I can complete this by saying that D and E, I already have AD, so I need CD, and then BD. I think that's the same. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so these are all the vertices that are adjacent to another one. And so that's what we mean by adjacent. They are connected. So E is only adjacent to D. That's all. Okay? Now, I'm skipping over things here a little bit. I'm sorry. The other question that I have that I missed here is this a connected graph? Now, what that means is that could I get on in a car, now think about this as a roadway, if I get in a car at A, can I drive all the way to E? If I can do that to every single vertex, not necessarily directly, but just so everything's connected, then I do have a connected graph. In this case, it would be yes. Where I would not have a connected graph is that if maybe I have F and G over here, out on an island. I can't drive from E to G and F because this is out on an island. So then that would not be a connected graph then, if I'm talking about all of this. But in the present state, yes, we do have a connected graph. Okay, now back to this last part. We want to try to write this graph into an adjacency matrix. What that means is that we're going to set up a matrix with all the vertices. So I put all these vertices out like this. Now, is A connected to A? You'll find out that sometimes that can happen, but in this case, it's not. So if it's not connected, then I'm going to put a 0. Is A connected to B? Sure. And this is an adjacency matrix, so when I say that, when I say connected, I mean they're adjacent to each other. So what I'm going to do is I'm going to put a 1 there. Is A connected to C? Yes. A connected to D? Yes. A connected to E? Ooh, I don't see that, so that's a 0. So then what happens to is I get the symmetry here. So if A is connected to B, B must be connected to A. So I can go down here just as I did it going over like that. So this is going to be what we call a symmetrical matrix. Not all these adjacency matrices are symmetrical, but if it's simple like this, yes, they will be symmetric. So down the diagonal, none of the points are connected to themselves. C to B. It's a lot easier if I look at the picture, so I'm going to get the picture up here. Is C connected to B? No. Is B to D? Yes. Is B to E? No. Okay, go ahead and finish this, and I'll finish this, pause, and try to look at this. So here's what I ended up with. Now what happens is that this is kind of nice because I can just say, how many vertices is E adjacent to? And I look across here, only 1, and that's vertex D. And so that's how I can read this. How many vertices is D adjacent to? 4. It looks like it. 1, 2, 3. Oh, did I do one too many? C and D. Yeah, this C and D is, I'm crooked there, but they are connected. So that's 4. Okay? So that's what that tells me. So if I added up these rows, it would tell me how many edges, how many vertices each one of these respective vertices are connected to. Now, this gives you a little introduction. You must go ahead and read section 4.3, and then you're going to do the problems. But make sure that you read the section first. It gives you some different practical exercises in there. All right, thank you very much, and enjoy the work.